my name is Rob Reynolds. Welcome to College Algebra Section 6.4. We're going to introduce logarithmic functions today. And I'm just going to pour everything out on you from the get-go, and then I'll try to break it down for you. So first of all, we have the definition of logs. If you ever see a log, then you can set it equal to y and change it into an exponent. And I call this the fish hook. B to the y equals x, because this kind of looks like a fish hook here. So b to the y equals x. So we'll say fish hook this. So there's the definition of logs. Then we have three properties of logs, which says the log of the product of a and b is the log of a plus the log of b. And the second property, log property, is the log of a divided by b. And since it's a division, it's the difference. So when you're multiplying, you add it up. When you divide, we're going to do the log of a minus the log of b. And the third one says the log of, I'll do x to the a power, is we're going to bring this exponent down out front and call it a log x. And I can prove all these to you on your calculators, but let me give you the last one. It's called the change of base rule. So we got we have a definition, we have three properties, and then we have a rule, change of base. And the change of base rule says if you ever see a log that's not base 10, even if it's base 10, I guess you can apply the rule, then you could write it as the log of a divided by the log of b. So what's so important about base 10 is we have some understood numbers in math. X is equal to x to the first. The square root of x is equal to the square root of x. So I have this understood 1 and I have an understood 2. For logs, the log of x is equal to the log of x base 10. So whether I write the 10 or not, it's understood to be there. So again, this is another and if I use natural logs, we have an understood e. So again, here are some understood numbers, and we already talked about e in the last section. That's an Andrew Jackson number, 2.7, 1828, 1828. Don't get the second property. Oh, I went into this because I wanted to talk to you about, the log base 10, it's understood. So don't get the second property mixed up with the change of base. Many students have problems with these two. Be careful, the log of a plus b is nothing. You don't want to get that confused and say that that's the log of a plus the log of b. That's not true. And you don't want to get mixed up that the log of a minus the log of b, where I have two logs here. You can rewrite it as one log, but you cannot apply that to this. These two things students try to combine all the time, and it's simply just not true. So this does not equal, this log of a minus the log of b does not equal this. And students will try to say that they are equal, and I'm going to give you a warning, be careful. The log of a divided by the log of b. If you see two logs, you can write it as one log. If you see two logs, you can write it as one log. But if you see two logs, don't write two logs. All right, so here comes some the book definition. Again, if you ever see a log, you can write it as an exponent, because logs undo exponents. Again, there's that fish hook, a to the y equals x. Their fish hook is going backwards. I would have written it the other way. Again, backwards fish hook, 3 to the y equals x. And this says 5 to the y with a backwards fish hook. So there's my fish hooks over there, and there's my little fish, so you can see. So change of base. Let's see. Yeah, this is all interesting. This is a to the. Let's get to some real problems here. A to the 5th equals 4. So all you're basically doing is writing an equivalent expression for these changing exponents. I didn't actually do this. This is kind of interesting. Let's change this exponent into a log. So the base of the exponent becomes the base of the log. And be careful when you write these. It's pronounced the log of, and then remember, logs equal exponents. So the exponent here is b. So I'm going to set logs equal to my exponent, in this case, b. and that leaves the 9 here. And then we could check it by using the fishhook. So e to the b equals 9, and that's what that says, e to the b equals 9. So this is red, though, the log of 9 base e. It's not red, actually it's the natural log because it's the ln. So this is red, the natural log, and natural log, it's log natural, but it's pronounced natural log. Don't pronounce it line. The natural log of 9 base e. I pronounce this log 9 base e. Don't pronounce it the natural log base e of 9. That takes too long, although it's correct. So if we were to set this equal to y and do the fishhook definition by getting rid of this log, or to undo a log, we change it into an exponent, and you can do that by 3 to the y equals 81. Then you can change that 81 to a prime base. I would choose upside down division. Pick prime numbers. That goes into 81. That's 3. Goes in there 27 times. There goes in 3. Goes into 27 9 times. So 81 can be written as 3 to the 4th, and this is what we had done in the previous section. Then we could say y equals 4. Over here, don't forget about your x to the negative first property, which is your reciprocal property. So the reciprocal of 1/8 is 8 to the negative first. So let's first of all set this equal to y and do the fishhook and say 2 to the y equals 1/8. Then I'll apply this property, the reciprocal property. So the base is really 2 to the, I'll throw one more step in here so you can hopefully clearly see this. This is really 1 over 2 cubed, because 8 is 2 cubed. So then if I do the reciprocal, this is 2 to the y is 2 to the negative third, because when you see negative exponents, you put it in the denominator, but if it's in the denominator, so now you can put it in the numerator and change the sign. So the bases are alike now, so then the only way the left side is equal to the right is if y is equal to negative 3. The domain of a log function, we've already graphed exponential functions, but we know exponential functions go through the point 0, 1. So here's your exponential with your asymptote at y equals 0. Well, logs are the inverse of exponents, just like addition undoes subtraction, multiplication undoes division. Logs will help us to solve for exponents. When you don't know 2 to the what power equals 3, in order to solve this, you can do whatever you want as long as you do it to both sides. So we could log both sides, use our log properties, bring that x down front, and this will help us solve for that x. All we have to do is type in the log of 3 divided by the log of 2, and that decimal would be a good answer for 2 to that decimal should equal 3. So logs undo exponents. They are inverses. So the inverse of 0, 1 is 1, 0. Your first look at this. The inverse of y equals 0 is x equals 0. So instead of a horizontal, we have a vertical. They're inverses. And the same 3 factors that cause decay for exponents, which is a negative x, a negative a, and a b value between 0 and 1, those 3 decaying factors are the same 3 decaying factors for your log function. So there's your first look at a log, and notice we cannot take the log of a negative. The log of negative 3 is undefined. In fact, the log of 0 is also undefined because we have a vertical asymptote there. According to this graph, the log of 1 should be 0. So that's what this says. If you let x be 1, then y will be 0. And if you take the log of 10, we're going to get 1. And I can prove that to you. So if you're way out here, the log of 10, you're only up 1. So this doesn't go up fast at all. This goes as nice and flat, because this point is over 10 up 1. So guess what? The log of 100 is only 2. So again, you're way out to the right, but only up 2. And the reason why is because if you look at the fishhook here, the understood base is 10, so 10 to the first is 10. And the base here is 10, so 10 squared is 100. So all you have to do is count the zeros. If you have the log of 1,000, the answer is 3, because 10 cubed is 1,000 if you do the fishhook definition. Remember, your calculator does base 10. You can always just type those in. So they're saying that the domain has to be positive, and the range for this log function, well, again, it's easiest to look at it. It's all reals. It goes forever low to ever high. So all reals is the range. And finding the domain and the range of each of these, I'm going to skip that section. Graphing, we'll talk more about graphing. There's your exponential function. There's your logarithmic function. You have that nice line of symmetry about that y equals x that we talked about. Natural logs have base e instead of base 10. And there's a button on your calculator for the natural log, but you graph them just the same. So they're inverses of each other. So again, the fishhook, 10 to the y equals x is the definition. Just going through some more graphing. And logs are inverses. Here we go, solving. This is where I wanted to go. So to solve for this thing, we would say 2 to the third, because I got to undo this log. So you would say 2 to the third equals 2x plus 1. So this is 8 equals 2x plus 1. I'll subtract 1, I get 7, and 7 halves is equal to x. A little bit of solving here. Same thing. To solve for this x, I would do the fishhook. X to the third equals 343. And I would probably, to undo this, since this is not an exponent, I would probably just take the cube root of both sides. What is that, 7? I don't know. You can do that in your calculator. 7 times 7 times 7. Skip this and see. Well, that kind of finishes that. So we have some exponential formulas. Let's see. The exponential was a times b to the x minus c. There's the graph. The asymptote was always at y equals d. Our start value, if you remember correctly, was at 0a, and then we had some decaying factors, which was the negative x, the negative a, and the b value between 0 and 1. Rules for graphing, boom, there they are. Wow, that was a little review from section 3.1. For 3.2, if you ever do see a log, we're going to set it equal to y and do the fishhook. And if the base is b, then I'll say b to the y equals x. So notice I'm changing a log into an exponent, just like you can change a subtraction problem into addition by adding the opposite. So to undo subtraction, if you had x minus 3 is equal to 0, you can undo subtraction by adding, and you can undo multiplication by dividing, and you can undo this log by changing it into an exponent. So a couple other examples. Set this equal to y. 2 to the y equals 32 if you do the fishhook. And let's change this to a prime base of 2. Many of you know that 32 is 2 to the 5th, so y is 5. 3 to the what power is 27? Some of you can do that in your head. 3 to the what power is 27? 3 squared is 9, but 3 cubed, so y has to equal 3. These are interesting properties here that we start getting in here. If you do the fishhook here, 5 to the what power y is equal to 5, and then y would have to equal 1 because we have an understood 1 there. It's interesting. It doesn't matter what it is. Every time the log of x, base x, if those are the same, the answer is always going to be 1. Even for natural logs. The natural log of e is also equal to 1 because notice the base is e, and whenever those are the same, the answer is 1. And the reason why is because e to the first equals e to the first. Over here, same thing, but now we have a 10. So I would say 10 to the y equals 100. We already kind of talked about this. Of course, y has to equal 2 because I have 2 zeros. And then if you ask for about the log of 1,000, repeating myself, you would say 3. This one's a little bit more difficult. 8 to the what power? So I would say 8 to the y equals 32. I would change this to 2 cubed because that is 8. This is 2 to the 5th. So 2 to the 3y equals 2 to the 5th. 3y has to equal 5. And finishing this off, then y is equal to 5/3. Looking at this other one, oh, the log of 1, we know that from the graph. The log of 1 has to equal 0 because that's the point on there. But if you wanted to do the fishhook, we can. 10 to the what power equals 1, and of course 10 to the first. does not equal 1. Because 10 to the first is 10, so, but 10 to the 0 equals 1. Anything to the 0 power, those are your exponential properties. So, which says anything, x to the 0 equals 1. So this time, y equals 0, which we already knew, because the log of 1 has to equal 0 because of my graph. So again, here comes some nice log properties. Every time you see the log of 1, I don't care what base it is. It can be base A. The log base A has to be 1. Some other properties, at any time that these are the same, the log of 5, base 5, that also equals 1. This is kind of interesting because this is a log with an exponent. If you jump that out front, this is equal to 1, and it's x times 1, which is just x. So that's a neat little property, which creeps up from time to time. And then the last one says the log of this is equal to the log of that only when x equals y, or this equals that. So it's kind of like you're unlogging both sides. So again, whenever this is equal, then we're going to get the log of 1 here because b to the first equals b. And whenever you see the log, as long as these are equal, then the answer is here just going to be x, whatever value that is. There are some examples. I'm going to skip those. This is the log of this equals the log of that, so x just equals 12. Here are some graphing of some logs. So all logs start at 1, 0. I'm going to give an asymptote at x equals 0, and I'm going to graph this by giving some growth because there's no decaying factors. And notice that the exponential function that we had graphed the previous section goes through the point 0, 1, and it has y equals 0 instead of x equals 0, and it has growth. So you have that nice symmetry about that y equals x. So looking at your graphs for your logs compared to your exponents. This is your graph. This is important. If the x value is positive, you start at 1, 0. If the x value is negative, you start at negative 1, 0. That's the only difference. So this x is positive, so I'm going to start at 1, 0. But I'm going to shove this horizontally, shifting 1 unit to the right. So the point here is actually at 2, 0. My asymptote is also x equals c. So it's going through that open dot. It's at x equals 1. But it has growth because there's no decaying factors. And this one, again, since the x value is positive, I start at 0, 1. I'm going to move 1 to the right and 2 down. 1 right and 2, move that open dot, 1 right and 2 down. The asymptote's at x equals c, in this case, right where that open dot was. In this case, x equals 1. And again, this looks like growth because I don't have any of the decaying factors being what? The negative x, the negative a, or the b value between 0 and 1. The same things that cause decay in exponential functions. None of that is happening, so I would go for growth again. This one, since it's a negative x, we're going to start at negative 1, open dot. In fact, I'm going to close that dot because there's no c shift or d shift. The asymptote's at x equals 0 because there's no c shift, and this is going to be decay. And decaying functions start up high and head down low, and it really, in all actuality, it probably looks a heck of a lot more like this because we know that the log functions don't increase very much. But again, I'm just asking for some nice sketches here, and I don't want you to stress too much about what that looks like. I'm looking for a point, and this point's going to be at positive 1, 0 because x is positive. The asymptote's at x equals 0, and this is going to be decay because you have a negative x. So again, and remember, this probably is going to not go real deep. It's probably going to plateau fairly quickly because remember, the log of 100 is only 2. So this one's going to be decay as well, but I'm going to start at negative 1 because I have a negative x is this property. The asymptote's here, and this is going to cause some decay as well. So start up high and head down low. So these are both decaying functions. Remember, if you have two decays, this is decaying because it's a negative a. This is decaying because it's a negative x. If you had both a negative a and a negative x, that would cause growth. This one's going to start at negative 1. It's going to be shoved 2 units to the right because 2 minus x equals 0 when x equals positive 2. And the asymptote's also at x equals 2, x equals c. And this is going to be decay because I've got a negative x, only one decaying factor, so start up high and head down low. So that's how to do some graphs. And the natural logs, remember it's base e. So if I set this equal to y, I would say e to the y equals 1 over e. So I'm really asking e to the what value is e to the negative first, and of course that would be y equals -1. The properties for logs are exactly the same, or excuse me, the property for natural logs is exactly the same as the properties for logarithms. It's just instead of base 10, we have base e. So you should be good with all of those definitions. And the graphs look the same in my book, natural logs or logs, because I'm not worrying about too much. Again, I've got a worksheet. This is going to start at 1, 0. If you'd like this worksheet, email me and I'll shoot you a blank copy of this. So 4 to the right, and this is going to go 1 up. So from the open dot, 1, 2, 3, 4, and 1 up. The asymptote's at x equals c, in this case x equals 4, and there's no decaying factor, so I would give growth through that point. So start low and head high, and I think I have solutions for all these. So if you'd like to go through and look at these, you certainly can. This is going to be a decay function, 4 units right, no, excuse me, 4 left, and 1 down, and it's going to be decay. So again, this is starting at. So you take the open dot that starts at 1, 0, because x is positive, move it 4 left, 1 down, and the asymptote's going to be at x equals -4. That's always at x equals c, and that would be the graph of this. This one would be a decay because you have one decaying indicator, which is the b value between 0 and 1. So this graph starts up high and heads down low. This one would be, let's see, we've got a couple. We've got a decaying factor here, the b value. We've got another decay factor, and it's a -x, which means we start at -1. This is going to go 5 units to the right, 3 units down. So take the open dot and shove it. 1, 2, 3, 4, 5 right, and 3 down. The asymptote's at x equals 5, right here, and it's going to be growth. So I'm going to start low and head up high because I have 2 decaying factors. Boom. There's my same graph. This one, I've got 2 decays, so that's going to be growth, sure enough. This one is going to be 1 decaying factor, and so it'll be decay. And this one, it looks like all 3 decays, so 3 decays make a decay, so start up high and head down low. So these are just examples. The start value here, remember, is not 1, it's -1, because you can't take the log of a negative unless you have a -x. Then, if I ask what's the log of, if you do a quick t-chart, what's the log of -1? Well, that's the opposite then. That's the log of the opposite of -1, which is back to just the log of 1, which we know as 0. So that's the only time you can take the log of a negative is if you have a -x. In fact, let's just say you can never take the log of a negative, because this isn't really negative, because it says take the opposite of that negative, which is back to positive. But remember, it causes decay. So this is going to be a decaying function, 5 units to the right, 3 units down, and x equals 5. This is looks like a growth, because you have 2 decaying factors, so you should have start low and head high. So that will finish up our introduction of logs. I hope that's helpful. Email me with your questions. Thank you.